Hello everyone, and welcome back to the series on multivariable calculus. Today we're going to be introducing one of the more important mechanisms associated to multicalc, and that is the partial derivative. So what exactly is a partial derivative? Well, if you don't know what a natural derivative is, or sometimes people call it a total derivative, then a partial derivative will seem very daunting at first. So what is a total derivative, or if you just know only one type of derivative, just the ordinary derivative of a single variable function f of x with respect to that function, that variable x. So we usually define this as a limit as, say, some parameter epsilon goes to 0 of the difference quotient f of x plus epsilon minus f of x all over epsilon. So what exactly is this? So one of the main goals that we were associated to in the realm of single variable calculus was finding how a curve is changing at a particular point. So what we did was we looked at a point in the immediate future, or potentially immediate past, or both, and then we considered the secant line through those points, and then we sent that distance between those points, epsilon, equal to 0, and then that approached what we call the tangent line slope at that point. And the slope of that tangent line we refer to as the derivative of the curve at that point. And we, of course, describe several properties and ways of calculating that particular slope given a particular family of functions. So the natural question one can take, especially since we're looking at multivariable functions, is the following. So what if f, instead of sending r to r, what happens when we send rn to r, in particular with n greater than or equal to 2? So let's look at a particular multivariable function of 2 dimensions, because if you can do 2, technically you can do all. So let's assume fxy is equal to x squared plus y squared plus e to the x plus the natural log of y. So let's assume somebody asks you, what is the derivative of fxy with respect to x? And let's assume we're not introducing any new mechanisms. So when we do this, what are we going to do? So we can take derivatives of other functions with respect to x by implicit differentiation. So the derivative of x squared with respect to x we know is just going to be 2x. The derivative of y squared will be just 2y times the differential of y divided by the differential of x. And then the derivative of e to the x will be e to the x. And the derivative of natural log of y will be equal to 1 over y times the differential of y divided by the differential of x. And that is df dx. So df dx. Now notice we have 2x plus e to the x, which is the term that only depends on x. And then over here we have 2y plus 1 over y times the differential of y over the differential of x. Right? And that was df over dx. Now, if we pretend just for a moment that the variable y was constant in all of this, so if y is identically equal to a constant, then the derivative of that constant with respect to x will be precisely equal to 0, and this term will completely vanish to 0. So if we do that, then the derivative of f with respect to x when y is set to be a constant will just be equal to that first term, 2x plus e to the x, which technically could still have y in it, right? So we have 2x plus e to the x. This object is what we refer to as the partial derivative. So the partial derivative of f with respect to x, which is just another way of saying, i.e., y is held constant. Right, so we're technically only looking at how f is changing with respect to the x variable directly. Okay, so that's what we call the partial derivative. So we would like to introduce a new notation here, which is called the partial derivative, and we would write it as fancy d divided by fancy x, or some people say partial f partial x, and this will be equal to 2x plus e to the x. Right, so that's what we refer to as the partial derivative of f with respect to x. Now, let's look at just a couple other examples. Let's look at a second one. Let's assume that we have f of xy is equal to 5x squared y plus 6 times the sine of xy. And let's assume that somebody asks you, what is the partial derivative of f with respect to x. So this is where we're going to hold y constant. So if y is a constant, then 5y is the constant of x squared. So that's just going to be equal to 10xy there. And since y is a constant, that's sort of like the derivative of sine of 5x. So that constant is going to come out via the chain rule. So we're going to have plus 6y times the cosine of xy. So what about the partial derivative of f with respect to the other variable, say y? So here we're going to hold x constant. So if x is constant, that means 5x squared is a constant with respect to y, and the derivative of a linear function y is just that slope. So that's just going to be equal to 5x squared. And here, x is going to be the constant, so y is going to sort of stay inside, x is going to come out, and we're just going to be left with 6x times the cosine of xy. And that gives you the partial derivative of f with respect to x, and the partial derivative of f with respect to y. And some people will introduce another notation. Some people write this as f little x as a subscript, and f little y subscript of xy. And that's how we can do partial derivatives. Now, I sort of just created this, and I didn't really formally define what a partial derivative was, because, for normal derivatives, we have a limit definition. So does there exist a formal definition of partial derivatives? And indeed there is. So the partial derivative of fxy with respect to x, and you can extend this to more than two variables if you would like. It's the same approach. This is going to be equal to the limit, as epsilon goes to 0, of f of x plus epsilon y minus fxy over epsilon. So we say that this, for a particular value of x, for arbitrary epsilon, typically positive, we say that the partial derivative is equal to this number, the limit, provided that the limit exists. And the partial derivative of f with respect to y is also defined as another limit. The limit as epsilon goes to 0, not necessarily the same epsilon, so you could use like epsilon x and epsilon y. So we can do x of y plus epsilon minus fxy all over epsilon. And if you remember anything about derivative approximations from single variable calculus, there also exists a backwards definition and a central definition with the same exact orders of approximations for accuracy. Just in case you don't want to analytically find partial derivatives, you just want to numerically approximate them. So those are the definitions for f sub x of xy and f sub y of xy. So just one slight comment in case you're curious. Let's assume that our function r maps r to r, and let's assume that our domain variable is x. Then df dx and partial f partial x are identically equal to one another. Right? So that makes sense because there's no y to sort of make constant. So what exactly does partial derivatives represent? So let's consider a two variable domain function. So let's assume that this is f, x, y. And let's assume that we have sort of like a bell curve in the x direction. And let's assume that we have sort of this curve in the y direction. Let's actually assume that it sort of curves up, and then it's sort of going like that in the y direction. Okay, so this is pretty much in the y plane. And this green curve, let's assume, is in our x plane. All right, so how can we interpret the partial derivative? So if we only consider this multivariable function in the x cross-section, then what you're actually going to see is that this curve is actually going to be decreasing in that particular direction. So we said that the partial derivative of f with respect to x will be less than 0 at this particular point. But if we look at things in the y cross-section, where we have this particular issue, and if we sort of look at that from the angle, let's assume that this is the point of reference so you can sort of see how I'm looking at this. Then what you're actually going to see for that particular line is that the partial derivative will be positive at that point. So partial derivative f with respect to y will be greater than 0 at that particular point. And you may be thinking to yourself, well, okay, we can find how this function is changing in the x direction. We can find out how this function is changing in the y direction. Can we choose an arbitrary other direction? For example, maybe we want to go in that direction that's pointing towards in that direction of a vector, let's say. And indeed, you actually can. Those are called directional derivatives, and we'll talk about those at a later time. But for now, let's just focus on our partial derivatives of f with respect to x, y, z, or whatever other variables you might have in your function. So just like in the single variable world, we can also do higher order derivatives of functions with respect to x, y, and z, just like we did before. So let's look at just another numerical example just to make sure we understand how that would look like. So let's assume that we have f of xy is equal to x squared y plus x cubed y plus sine xy. If we were to do a total derivative of this particular function, you would have 3 iterations of a product rule, where one of those products would be in a chain rule for that sine xy term. But in the realm of partial derivatives, it's actually a lot easier. So how would that look like? So the partial derivative x, f of x with respect to x, that's going to be equal to what? So here y is a constant, so we're going to have 2xy. And then with respect to x again, that's going to be 3x squared y. And with respect to x for that, that's going to be equal to, so y is going to come out, and then cosine of xy. And if we take the second derivative with respect to x, again, y is still a constant. So if that's a constant, then we're going to have 2y as the constant, so we're just going to have 2y. And then we're going to have 6xy. And then we're going to have minus y squared times the sine of xy. So that's going to give us the first and second order partial derivative of f with respect to x. Now, how would it look like for y? So fy, xy, will be equal to, so x is going to be a constant, so we're just going to have x squared. Again, we're going to have x cubed, and then since x is a constant, x will come out, so we're going to have x cosine of xy. And if we look at the second order partial derivative, that's going to be equal to what? So x squared and x cubed are just constants, so they differentiate off to 0. And x is going to come out again for our cosine function, and we're just going to have minus x squared times the sine of xy. So those are going to be the first and second order partial derivatives with respect to y. So can you mix the partials? You know, instead of xx and yy, can you do xy and yx? Indeed you can. So let's sort of look at that and see how that would go. So let's bring back our function again. So fxy was equal to 2xy. And let's assume that this is the partial with respect to x, so 2xy plus 3x squared y plus y cosine xy. And let's discuss how we would define fxy xy. So by definition, this is going to be equal to the partial derivative with respect to y of fx xy. So what would that be? So that's going to be equal to the partial with respect to y of 2xy plus 3x squared y plus y cosine xy. And we differentiate with respect to y partially. That means x is a constant. So what are we going to have? So with respect to y, x is a constant, so we're going to have 2x as our first term, and then we're going to have 3x squared for our second term, and then we're going to have minus xy times the sine of xy for our next term. So that's fxy xy. Okay. Now what about the other direction? So if we look at fy first, and remember fy came out to x squared plus x cubed plus x times the cosine of xy. Fyx will be equal to what? So fyx will be equal to the partial derivative with respect to x of fy xy. Right? So that's going to be again the partial with respect to x of x squared plus x cubed plus x cosine xy. And keep a note, you know, fy and fx were different functions, right? But when we take the derivative with respect to x here, we're going to have 2x plus 3x squared, and then minus xy times the sine of xy. And we got, this is going to be fy xy. Right? See anything interesting here? you should see that fxy and fyx are equal to one another. So the natural question that you may ask, well, maybe I would do the easier one first and then the easier one second, but you should be careful because you don't know if that's always true or not. So is this always true, that fxy equals fyx for all f? And the answer to this question is sadly no. So there's a theorem that guarantees when this is true. And the theorem goes as follows. And sometimes people will refer to this as Clairaut's theorem. C-L-A-I-R-A-U-T. And it says the following. Now let's assume that this function f maps R2 to R. Now technically speaking, it doesn't have to be R2 to R, it could be R15 to R, but since we're only focused on two variables, x1 and x2, let's say, we can take it without loss of generality that this maps R2 to R, but it can technically be presented in terms of, higher dimensions if you wish. Let's also assume that this function's second order partial derivatives, fxx and fyy, are both continuous in some region, where this region is an open neighborhood of some point AB for which you're interested in finding the second mixed order partial derivatives at that point. Then, regardless of the order you take, you're going to get the same exact value, right? So in order to guarantee that it gives you the same value, just take the second order partial derivatives and make sure they're continuous at that particular point, i.e. the limit equals the function value at AB. Let's consider a couple examples that I actually think are quite interesting. The first example that I want to look at is fxy is equal to x squared y divided by x to the power of 4 plus y to the power of 2 and 0, provided that xy is not equal to 0, 0 for the first, and xy allowed to be 0, 0 for the second. So what I want to do actually is look at this particular function from the x and y directions and analyze. So if I take the partial derivative with respect to x of this function, what am I going to get? So via the quotient rule, I'm going to have what? So I'm going to have the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So it's going to be x to the power of 4 plus y squared squared. Right? So that gives us that particular object. And if I allow, for example, y to be equal to 0, I'm going to have fxx0 to be equal to, so the y squareds is going to go away, that's going to go away, and I'm going to have 0 divided by x to the power of 4 plus 0, which we know is going to be equal to just 0. So we can actually just cancel that out. So that's going to be 0. Also, if we let x 0 y be the case, so keep in mind everything has y in it as well, so that's also going to give us 0. And you should also be able to verify the more general result that fx and fy are actually defined for all x, y, and R2. So the first order partial derivatives are actually continuous for all inputs x, y. But what's actually very strange is that this function is actually discontinuous at 0, 0. So we have a discontinuous function whose partial derivatives are continuous everywhere, which I actually find quite, I don't know, on the surface strange, because in the single variable world we actually don't have that phenomenon, but in the multivariable world we do. Another example that I find quite interesting is the following. Fxy defined to be equal to xy cubed y minus xy cubed all over x squared plus y squared, defined on the point where xy not equal to 0, 0, and 0 when it does. Right. So again, we have this partially defined function. One thing you should be able to show is that if we look at fxx and fyy, fyy are not continuous at 0, 0. Right, so that's the first thing that you should be able to verify. And keep in mind what we mean by that. That means that the limit as xy approaches 0, 0 of x cubed y minus xy cubed all over x squared plus y squared does not equal to the function value at that particular point, in this case 0. Right? So you should be able to verify that particular object. And keep in mind, this is not your fxx and fyy, so make sure to replace that with fxx and fyy once you are able to find them after 2 iterations of the quotient rule for each. So if that's the case, that means the Clairaut's theorem does not guarantee the equality of mixed partials. In particular, what we actually come up with when we actually look at fxy and 0, 0 and fyx of 0, 0. Now keep in mind, Clairaut's is not a necessary and sufficient condition, but if we have this particular case, then fxy at 0, 0 actually comes out to be 1, and fyx actually comes out to be minus 1. So we actually have different values when you change the order of partial derivatives, right? Keep in mind, Clairaut's theorem guarantees that if the second derivative partials are continuous, then the mixed partials are equal to one another. And when we don't have continuity of second order partials, then the mixed partials could be unequal to each other. And here's an example of that. And I leave you, these as exercises to show because definitely they are algebraically intensive, but that's more of a single variable calculus exercise. Anyway, I hope you enjoyed this video on an introduction to partial derivatives, and I hope to see you in the next one. Take care.